Welcome to the next video in the Systems Programming video series. We are moving on to Chapter 7, talking about assembly language. In particular, we'll be learning about the X86-64 instruction set architecture. So what that essentially means, what distinguishes this particular ISA from others like RISC-V and even other things in the x86 family, is the specific commands that are in the language, right? And that corresponds to the ways that you are permitted to manipulate bits and bytes of the memory. And part of that is having certain things that are called registers, right? In order to do this, it's going to be really useful for you if you have a machine that has an x86-64 processor, and you can check that right on my Linux computer. I pulled up a terminal just to make sure that that's what I have. I was almost certain of it already, but just to really confirm, you pull up a terminal, you enter this command, and it should print out that right there, telling you that you have x86-64. Now, x86-64 is building off of an earlier architecture, IA32, and that was for 32-bit memory. The fact that 64 is built on top of 32 is going to be important for someone understanding how x86-64 works. There's a lot of inherited legacy that probably would not be the way that it is if we developed a processor from scratch. I was watching a video a little while ago where somebody told an anecdote that one of the people who works at Intel, because ISA is developed by Intel, and said that at Intel, anybody who gets an instruction, like if you design a new instruction that goes into the chips that they distribute, you become like a fellow or something like that. And what this has meant is that everybody is working to create new instructions and nobody is working to remove instructions. So as you look at the manuals for the Intel ISAs, the manual keeps getting bigger and bigger as they add more and more things, and it is becoming somewhat bloated with essentially no sort of institutional pressure to try to remove things. And that might be some amount of why maybe this ISA is not quite as performant as RISC-V and certain other things. That's a bit of speculation. I don't really know that for a fact. But certainly it is interesting that by contracting the set of instructions, in RISC-V having fewer instructions, you get more performance, is certainly interesting. So what we're going to do for, I guess, the rest of this video, which is to say this section 7.1, is we're going to study this C program, this extremely simple C program, where all it does is it has a main function. It assigns a variable int the value 40. It passes x into this function adder2, where all adder2 is simply returns that value plus 2. So I think it makes sense that this line, without thinking about assembly, just understand that x is given a value that is bigger by 2, we then call to print it and we return 0 in the main function. So this is an extremely simple C program. We all know what this does basically, but what we're going to try to do is to learn how this works at the level of assembly. So one way to view the assembly code is to compile the program as you normally would and then call this objdump command, giving the -d flag. Notice that you call this on your object file, the adder, not the adder.c, not the source file. But so you call it, and it goes into whatever file you say here, right? So here we're calling it output. You could call it whatever you want. But that's what this line does. It basically just does an object dump, which effectively just puts all of the assembly code into the output file. The word less is a command built into just about any Linux terminal, and will try to print out a minimal, just a few lines, right? Not the whole thing, right? If you called cat or certain other commands that try to, preview the content of a file, it may give you so much information that your terminal doesn't have space for it, and you have to like either scroll around within the terminal, and it wasn't really made for that. So anyway, the point is that calling less tries to give a small amount of information that fits somewhat neatly inside of the terminal. And so we are basically just printing the content of output, but we're trying to do so in a somewhat manageable way by calling less on the out. Now, what this probably, right, because this is going to have a ton of information. If you went and looked directly at the file in whatever text editor you prefer to look at a very large text file, you'll see that it's very large. And we would like to skip to the portion that talks about the adder2 function. We basically want to see the assembly code associated with this function, just to keep things simple and go straight to the point. So what you can do is immediately after you have typed less, you can type /adder2, skip down to that portion of the printout. And so you should see something like this. It's got memory addresses like this here. This is basically a shortened code of a memory address, and so is this here. So you'll see memory addresses that are not the same as the one that's here, right? You should see memory addresses, but they should not necessarily, in fact, they almost certainly will not be the same ones that you see here. Are hex codes that correspond to the commands over here. But we're not going to worry about the hex codes too much because we're, at least at this sort of like high-level overview, more interested in understanding this over here. And so, by the way, I guess I should say explicitly, this is the assembly code. So if you've never seen assembly before, here it is. Now you've seen assembly. And so whenever your C code run, or like whenever you compile C code, the compiler, I mean, all the compiler does is it takes your, well, maybe not all that it does, but one of the main things that it does is it takes your C code and turns it into this. It turns it into assembly. Now, we maybe don't want to talk right away about all the details of what's going on here, but I guess one thing that's probably important to start saying is that these are the, addresses or names of registers, right? So RBP is a register, RSP is a register, EDI is a register, basically, yeah. And these are commands that take in some arguments. The push is basically a function, and the argument to the function is this register. Now, throughout, it is going to be important to distinguish between the address of a register and the value of a register, right? It's the usual distinction between the address of some variable or data or whatever and the value that is stored at that address. So when you see this %RBI, that is the address of register RBI. So it tells us where to look in memory to find it. And by contrast, whenever you put parens around a register, you're now talking about the value at that address. So with that having been said, I don't think I want to talk in any more detail about that just now. I'll just sort of wait until the book starts introducing it to talk in any more detail about these registers and commands and so on. Now, one thing that is worth knowing is that the addresses themselves, right, these addresses over here, are really 64 bits. Now, you wouldn't know that because these have been shortened. If you were thinking like, okay, so this looks like maybe this is hex code, I suppose, right? And if it's hex code, then every hex takes up 2 to the 4 bits. And so every 2 hex codes is a byte. And so how many bytes does it look like we have here? It looks like we have 3 bytes. And if you have 3 bytes, or maybe let's think about it conversely. If you have 64 bits, right? If these addresses are stored in 64 bits, then how many bytes is that? Well, let's take 64 divided by 8, right? Because a byte is 8 bits. So divide by 8, you get 8, right? So we're basically saying that addresses are stored in 8 bytes. But here it looks like we only have 6 bytes. So, of course, that's because these addresses in the textbook have been shortened for readability. And so, okay, so that's the comment about the addresses. This number 55 is, essentially the code for push RBP, right? So I guess for some reason that gets a single or a pair of hex codes to encode that one command, the whole thing. And push RBP happens basically at the beginning of every function call. So maybe, why does that get its own special, seemingly just a single pair of hexes as opposed to everything else, which seems to get many more hex codes for a command or something like that? Maybe this one only, right, like it comes up so often that we want to give it a simple code. That's my guess. I don't know that for a fact. But this one, you could imagine the 48 corresponds to move, and the 89 corresponds to the stack pointer, and the E5 corresponds to the base pointer at this point. Yeah, it is worth knowing that, because this is what is this? Like a complex instruction set, something, computer or whatever, that this is not like a one-for-one between that's, I think that's independent of this. But in any case, so C, right, there is not a one-to-one correspondence between code in C and assembly code. So a single line in C can sometimes cause multiple lines of assembly. And by the way, it's worth knowing that it is relatively easy. Compilers do it every day. Take C code and turn it into assembly. That's like an easy direction. But going in reverse is generally not feasible. People have tried to create these, like, what do they call them? I think disassemblers or something like that, where you feed it in assembly code and it, tries to reverse engineer the original C code. And it never comes out the way you want it to. They run very slowly. They get, C code that like nobody would write. So in any case, there's like an easy direction and a hard direction, right? Compiling is easy. Our compilers do it all the time very quickly. Going in reverse is not easy. And it's all kind of part of this fact that there is not a one-to-one correspondence between C code and assembly. So registers are a word-sized storage unit located directly on the CPU, right? So because it is directly on the CPU, that kind of means two important things right away, which is that it is very fast. Things that are on the CPU run extremely fast, but also that they are unstable. If the power is cut from the computer at any given moment, whatever is in the CPU is lost at that moment. So that's probably just worth keeping in mind. But so registers are storage units located directly on the CPU. The Intel CPU has a total of 16 registers. We are perhaps not going to be concerned with every single one of them, but there are some that are especially important for us. So, well, I guess we'll find out what those are in a bit. You can see several of their names here. Yet it is important to know that while we care very much about addresses and integers, as far as the registers are concerned, it does not know the difference. So if a register contains some value, whether that value is a number that is meant as an address of some place in memory or something like that, or if that value is just supposed to be some number used in the program, the register makes no distinction between these, right? I guess another way of saying this is that there are no types as far as the register is concerned, right? In C, you declare types and it enforces a certain kind of consistency, and it also dictates, like when you perform operations, how are the operations performed? The types govern that kind of behavior, but in assembly, there's no such high-level thinking about types, at least not done by the assembly language itself. Okay, so the first and one of the very, very important registers is the RSP, the register stack pointer. So the stack pointer, right? So we've talked before about how you can have a stack diagram where main is usually on the bottom, and you may have some function call, like maybe adder2 or whatever. And in this stack diagram, well, this kind of information has to get maintained by the pointers to addresses in memory. And so what you really want to keep in mind throughout is that the top of the stack, we try to maintain its address with RSP, right? So the stack pointer is pointing to the topmost address of the entire stack, so that if we ever need to add a new thing on top of the stack, we know approximately where to do that. So that's the stack pointer. Now there's also the base, or RBP, the base pointer, and the base pointer points to the bottom of the active stack, right? So if this thing is the active stack, then RBP should point to its very first location in memory, right? Notice that this diagram, what does this diagram now mean? I'm trying to draw regions of memory with addresses. Well, actually, I should put a downward arrow like this, where somewhere up here is the address 0 that is allocated for the entire program. Addresses become larger and larger. Up here, there's I'm sure we'll see this diagram earlier. But anyways, these are large addresses, and they run from 0 at the initial address of the program up here down to larger addresses, and like this region is used for like heap memory and stuff like that. But keep in mind, I think we've talked about this before, that as the stack grows, it grows up toward the other, the rest of the program addresses, right? So the stack grows that way towards smaller addresses, which can sometimes be confusing. But anyway, okay. So because we will so often need to remember the meanings of these various registers, I thought it was maybe a good idea to just make a little note that we can frequently pop up if we need to refer to it, reminding us of what the meanings of these various register names are. So percent RSP, oops, what am I thinking? Is the stack pointer. RBP is the base pointer. And just to reiterate, the stack pointer is at the top of the entire current stack. The base pointer is at the bottom of the current active frame, right? I'm sort of trying to diagram this as adder2 being the current active frame, the most recently called function. Okay, so there's RSP and RBP. Now, here we see that these addresses, RDI, RSI, RDX, RCX, and so on, which the names are just nonsense. Like, one of the worst things about this is that we're just inheriting names that made sense a long time ago, but as the ISA grew from, whatever it was, 16 bits to 32 bits to 64 bits, the names cease to make sense with these changes, but we keep using them anyway. So I don't know that there's a logic behind why the RDI is called what it is called, right? That it's called RDI, but what we use it for is the address of the first parameter. Adder2 we saw has a single parameter in that function, and so RDI would be the register that is used to hold that parameter, right? The one parameter of the function, and presumably throughout the run of the function, all other things, right? They're supposed to hold the addresses of the other parameters, but if there's only one parameter, then you wouldn't use these, and they would presumably hold junk values that you should not access since those parameters don't exist for the function. But that would only be for adder2, right? When there's only a single parameter to the function, right? When you have functions with more parameters, you get more registers. And so for the most part, right, we're mostly just going to be dealing with single argument functions. So let's just make a note that RDI corresponds to the address of the first parameter, and we won't worry about the others. Let's also notice that RAX, also very important, stores the return value from some function. So let's make a note of that. That will be frequently important. So RAX is return value. Also somewhat important is RIP. That is the instruction pointer. You'll see this in action in a little bit, but that indicates the address of the current thing that we are executing at any given moment in a run through the assembly program. So let's make a note of that. I decided that this video was running a little long, and so I decided to cut it here, and we'll pick this back up in the next video.